The idea that matter is made of atoms has been around for many years. As we currently understand it, there's a connection between the identity of an element and the amount you can have. So, for example, if we have the mass of a hydrogen atom as 1.67 times 10 to the negative 27 kilograms, you can't have 2.5 times 10 to the negative 27 kilograms. You can have any whole number of hydrogen atoms, but you can't have a fractional number. This is kind of like if you bought candy by weight. Gummy bear supposedly has a mass of 3 grams, so you can't go to a candy shop and get 32 grams of gummy bears. You could get 30 or 33 or whatever. So the kind of candy is linked to the amount you can have. There are other candies that may only be 1 gram per piece. Now, this doesn't usually matter for us because the size of the atom is so small that, we don't deal with individual atoms anyway, but that restriction is there. And what nobody before the 20th century apparently considered was the idea that energy was quantized just like matter is. That means there's a smallest amount of energy, and the link here is between the energy of light and its color, or we could say its frequency. So if Newton had had electricity and dimmer switches, he probably would have predicted we could turn the dimmer switch down to an arbitrarily small value, regardless of the color of the light. Max Planck realized that the energies of the atoms and molecules inside heated objects, which are called black bodies, because we assume they're perfectly absorbing and therefore perfectly emitting. He assumed or realized these atoms and molecules could only have special values of energy, quantized values. Now, it may seem like if you pick up a block of iron, the atoms in there aren't moving and shouldn't have any energy, but they're all really vibrating back and forth constantly. The energy of an atom or an oscillator or whatever vibrating at a frequency f is some multiple of hf, where h is Planck's constant, and it has this ridiculously small value, 6.626 times 10 to the negative 34 joules times seconds. That is not a familiar unit of measurement for us. We don't worry about quantization of energy if we're talking about big things like baseballs or cars, where we might be talking about energy in terms of joules. So it's a little bit more reasonable for us to put Planck's constant into units of electron volts times seconds. And there, it's still ridiculously small, about 4.14 times 10 to the negative 15. So what this tells us is if we have this hot object and we add heat to it as gradually as we possibly can, the energies of the atoms are still going to jump up in stair steps. They'll increase a little bit at a time, not continuously. We could say the energy of the atom is some whole number n times hf. Now, where did this half come from, and what does that mean? This is what this tells us is even if we could remove all these quanta, these particles of heat energy out of the atom and make it go slower and slower and slower till we get down to the point where n equals 0, there would still be some energy associated with that atom, 1/2 of this fundamental value. And this is the reason why you may have heard we could get very, very close to absolute zero, but we can't actually get to it. We can't remove that last little bit of energy. Now, the size of the quanta, the energy steps, is this. The difference between one energy and the next is hf. So that means whatever energy we move into or out of the atom is going to have to be quantized in the same size units. Einstein used this idea to explain an old problem in physics called the photoelectric effect. And what this is, if you shine light on a metal surface, you can eject electrons from it. Remember that people were still talking at this time about is light a wave or a particle. If you look at the diffraction and interference experiments we looked at not long ago, it's obviously a wave. On the other hand, the photoelectric effect makes it look like light is obviously a particle, so this disagreement was still going on. If we want to explain the photoelectric effect, we have to explain the observations, and those are, for example, for each metal there's a certain frequency of light And below that frequency, you don't get any electrons no matter how bright the light is, so how intense the light is. So you might be able to get even very faint blue light to eject electrons from something, but even very bright red light won't do it because the frequency is lower. Another observation, there's no delay between when the light hits the metal and the electrons leave it. I don't mean we're violating causality or something in that it's instantaneous, but what it means is there doesn't have to be a build-up time where the light waves, if they are waves, are shaking the electron back and forth. The electron is soaking up energy and finally gets enough to leave. There's no time delay like that. Third thing, the number of electrons you get per second, which remember is a current, we'd call it the photocurrent here, depends on how bright the light is, not the frequency of the light, as long as you're above the minimum frequency in item 1. The kinetic energy of the electrons that get ejected, that does increase as the frequency of light increases. If we turn up the intensity, turn up the brightness, all we do is increase the current. We don't change the speed of the individual electrons. Finally, the kinetic energy of the electron that gets kicked out is connected to the frequency of light by this simple-looking formula. The electron kinetic energy is energy of light minus this thing, this phi. Sometimes you see this as WF for work function or BE for binding energy. It's a few electron volts. It depends on the material. But what this idea means, this work function, binding energy, whatever, it represents the fact that we can't just shake electrons out of metal. Even though the free electrons are not attached to particular atoms, they are bound to the metal itself. And that's what this work function represents. So the way Einstein explained all this was to say that the energy of a photon of frequency f is this, E equals hf. For example, we want to find out the energy of 750 nanometer red light. So this is about as red as you can see. Our energy would end up being 1.6 electron volts per photon. Now to calculate that, how do we get this number? First, we find the frequency associated with this wavelength. For that, we use c equals lambda f. So f is c over lambda, so speed of light divided by 750 nanometers gives us about 4 times 10 to the 14 hertz. The energy of a photon at that frequency is Planck's constant times the frequency. We get 1.65 electron volts. This is why we don't want to work in joules, because the energy of this photon in joules would be about 3 times 10 to the negative 19, which is really ridiculously small, and we can't understand it the way we can understand 1.65. If we look at the shortest wavelength we could see, which gives us the highest frequency and therefore the highest energy, it's about 400 nanometers. It's violet. We plug it in here, do the same math, and we get an energy per photon of about 3.1 eV. So if you've wondered why physicists are not really concerned about the electromagnetic radiation, that just the word radiation freaks people out, from cell phones or Wi-Fi or 5G is a common one, the reason physicists don't usually worry about this, you can find the energy per photon from them. So for example, your Wi-Fi is either 2.4 gigahertz or 5 gigahertz. The higher frequency has more energy per photon, of course, so we use that. We plug it in here, and we see that each photon from 5 gigahertz radiation is about 21 micro electron volts. That's way less than 1 eV. The reason this is significant, 1 eV, that's the ballpark for energies of chemical reactions. This energy is way too small to move an electron off of an atom, off of a molecule, and moving electrons around between atoms, that's chemistry. Now, the radiation that we would be concerned about as physicists, once you get to ultraviolet photons, they're all going to be more energetic than our violet that we found here, right? That was 3.1. They're all going to be more energetic than that. And above that limit, you get to the point where you can start knocking electrons loose from atoms or molecules, and that means you make ions. And for that reason, we call it ionizing radiation. If you keep going up in frequency, a lot of times you look at the per photon energy instead of wavelength or frequency. So, for example, X-rays at a dentist's office, they don't usually talk about the wavelength or the frequency. They'll talk about the energy. In a dentist's office, it may be something like 30,000 EV or 30 keV. Chest X-rays, CT scans, things like that, they can be over 100 keV because it has to get through a much larger part of your body. Gamma rays, and we'll see their origin at some point here in the future, but gamma rays usually have energies even higher than this, sometimes a few million electron volts. And these things can do a lot of damage as they go through your body. The idea of a photon as a bundle of energy instead of a wave train explains the photoelectric effect. So we see the energy carried by the photon is HF, and it either gets transferred to an electron or it doesn't. If it is, that's either enough energy to get out of the metal or not. If the photon's energy is greater than this work function, all the extra gets deposited into the electron as kinetic energy. So this handles observations 1, 4, and 5. For point 2, the energy is delivered all at once in a single packet, so there's no reason for there to be a delay. Finally, point 3, that's what we expect since each photon can only kick out one electron. The more photons per second, as long as we're above the work function here, the more electrons leaving per second, which is greater energy. Now, reasonable question to ask is, why can't we bump up the intensity and eject electrons even if HF is less than the work function? So, for example, work function for mercury, 4.45 eV. One violet photon is not enough to do this, so violet light wouldn't do it. If we could hit it with 2 violet photons, that would be 6.2 EV, and that would certainly be enough to do it. The problem is there's essentially no chance of this happening with the light intensities they had in the early 20th century. It takes a ridiculous intensity of light to get 2 photons to hit 1 electron at the same time. Really, 10 nanoseconds is close enough to the same time. But if you do the math, this is an impossibly short time for the intensities of light they had to offer. One interesting thing about sort of physics that's changed since then, lasers were developed in the 60s, and you actually can get a bright enough laser, an intense enough laser, for this to happen. So you could have, something like violet light hitting mercury and eject some electrons if the laser is intense enough. So this is not going to be like laser pointer. This is like big deal laser. But you can actually make this happen because you do have a good chance of getting 2 photons there at the same time. This is interestingly enough, this is the thing that Einstein won his Nobel Prize for, not relativity, not Brownian motion, not general relativity. He did several very important things, any one of which he could have gotten the Nobel for, but he actually got it for the photoelectric effect.